Hello, everyone. Welcome back to the series. It's been a little while, about 6 or 7 weeks now, since the last episode, but we are picking things up right where we left off. So, in this particular video, we are diving into the next part of the process. A lot has happened since the first episode, and this particular video builds directly on the foundation we set earlier. So whether you watched the last video and it came out a couple of weeks back, or you are just joining now, you are in the right place. So let's get started. So in the last video, we introduced operational technology and explored how OT environment differ from traditional IT networks. So in this particular video, we are going to build on that foundation by examining several core OT concepts and terms. So let's talk about industrial networks and industrial protocols. Uh, so these two are the fundamental building blocks of any OT environment, industrial networks and industrial protocols. So what is an industrial network? An industrial network is the communication backbone that connects industrial devices and allows them to coordinate their actions. So without this communication layer, each piece of equipment would operate independently, making it impossible to run a synchronized industrial process. So having an industrial network is a must in any OT or ICS environment. Next is the industrial protocols. This is the next logical question. How do these devices communicate with one another? So this is where industrial protocols come into play. An industrial protocol defines the rules, the structure for exchanging data between the devices operating in the OT environment. So, just as people need a shared language to understand each other, industrial devices they need or they require a standardized set of protocols to interpret and act on the information being set. So, some of the most commonly used OT protocols which you encounter in the OT or ICS environment are OPC, Ethernet IP, DNP3, which is Distributed Network Protocol, another is Profibus. Modbus is also very famous or most commonly used protocol. Uh, let's talk about the flow or different components. If you see this architecture diagram, there are many devices which are part of the ICS network. So field devices. Basically all the sensors, the actuators, the motors which are in the uh, running in the field, the PLCs, the controllers, the HMIs, historians, engineering workstations, uh, and also domain controllers, which is basically responsible to manage user identities and permissions, remote access terminal, which allows vendors or engineers to perform some remote maintenance, SIM systems to collect and analyze security logs. So this is all, I would say, part of the ICS network. And at the top, you will see a connection to the corporate network, which we are going to discuss in the next slide also. So this expanded architecture represents a more realistic picture of how today's industrial network operate, interconnected, layered, and supported by a range of systems for operations, for maintenance, for security. uh, the corporate network specifically, because any ICS environment rarely it exists in isolation. So every OT system belongs to a business, and that business requires email, administration tools, procurement and supply chain systems, public facing services, internal collaboration and productivity tools. So all these tools which I just mentioned, they reside in the corporate network, which is essentially a traditional IT environment. And in this particular architecture, the corporate network connects to the industrial network through a router or through a firewall, which we consider as a boundary. And while this connection is often necessary for production planning or for reporting, It also expands the attack surface because now we are enabling indirect exposure to the internet for the ICS network. So that's a very, very high level view of any industrial network and the convergence of IT and OT and how these two networks connect to each other. This is something we are going to discuss more in detail when we talk about the Purdue model in ICS word. Let's talk about zones, conduits, and perimeter. So these are, I would say, three of the most important concepts in OT security. A zone is a group of assets that share the same security requirements. Think of the physical world. A lobby is open to everyone. Office requires some key cards, or a restricted area which requires some special clearance. So that's basically some of the examples of the zones. So similarly for OT environments, they may contain zones such as, if you go back to the diagram, you have field devices. So you have a zone for field devices, control system zones where you have all your engineering workstations or historian PCs, uh, engineering workstation zone or historian or supervisory zone. So when we talk about zones, they are if you talk about any uh, famous OT uh, compliance standard, uh, let's say IEC 62443 standard, zones are heavily emphasized in the IEC 62443 standard, which is widely used in OT programs. So by grouping assets into some logical segments, we can apply appropriate protections based on the criticality of the device. What is a conduit? So once zones are defined, we need secure ways for them to communicate. So this is the role of the conduits, which is a controlled pathway that allow data to flow between the zones. So conduits can be a trusted conduit for interactions within the same security level. Uh, Untrusted conduits when connecting zones with different security requirements. Untrusted conduits typically require additional security controls such as authentication, encryption, access restrictions, or monitoring. So that's basically about conduits, and perimeter is basically the boundary around a zone. This is where most cybersecurity protections are implemented. Some of the examples of perimeters like firewalls, IDS, IPS, network filtering. Also, you have some compensating controls, especially in legacy heavy OT environments. Perimeters, they allow us to enforce consistent protections while respecting the technical constraints of industrial devices. Uh, if we talk about all these three important concepts, we have three broad zones, I would say. One is the control zone, the other one is the supervisory zone, and the third one is corp zone. So conduits define how they communicate with one another. You see the bold lines in blue color. This layout illustrates how segmentation and controlled communication paths create a secure architecture. But in real deployments, there are often many more zones, many more conduits, uh, and you will always have more boundaries at each of the layers where you have the OT device present. So this is more about zones, conduits, and perimeter. Uh, this is a pictorial view. Now we talk about the Purdue model. Uh, I would say one of the most influential frameworks in OT architecture. That's the Purdue model. It was developed in the 90s. So this model organizes industrial systems into hierarchical levels, uh, each with its own operational purpose and security needs. So you see there are different levels. Level 4 is basically your enterprise or corporate level, where you have all the business systems and corporate IT infrastructure. This is also where most cybersecurity threats originate because you see the connection towards the internet in this particular level. Level 3.5 that's the DMZ, that securely handles data exchange between IT and OT. So this particular level sits more or less in between your IT and OT. Level 3 is basically the site operations zone or supervisory zone. That's more at the global level, where you have the SCADA servers, your data servers, your central controllers. Uh, Level 2 is basically again a local area supervisory control, where you have the HMIs, engineering workstations, local supervisory systems. That's level 2. Level 1 is basically where you have all the industrial controllers like PLCs, and level 0 is the process level, where you have the sensors, actuators, all the instruments that interact directly with the physical processes. So the main value of the Purdue model is the clear security boundaries it creates. As you move up the levels, the real requirements decrease, which allows more advanced security controls to be implemented. Uh, Now let's talk about some of the myths about the OT security. Uh, there are some widespread misconceptions that often lead to poor security decisions. Legacy OT systems can't be secured. Uh, that's often a very common misconception. They can be secured using some compensating controls, especially at the zone perimeters. Nobody attack OT systems. That is again a common misconception. Attackers are increasingly targeting industrial environments. Examples: a famous Stuxnet attack to modern ransomware attacks against the critical infrastructures. OT security isn't my responsibility, so security requires collaboration across IT, OT, engineering, and management roles. So this is a shared responsibility. A firewall is all we need. That this is again a very common misconception. So OT security requires a layered defense in depth strategy. No single control is sufficient. OT systems are air gapped, so they don't need security. This may have been true, I would say, for few decades, but today most OT networks connect directly or indirectly to corporate networks, and therefore to the internet. So they are no longer, I would say, fully air gap. They somehow connect indirectly to the internet or to the corp zone or to the business or the enterprise zone, where you have a wider attack surface. OT security works the same way as IT security. Again, a very common misconception. While some of the concepts in OT and IT overlap, but OT has unique constraints related to safety, uptime, and legacy equipment that fundamentally change how security must be applied. So, these are some of the common misconceptions when we talk about OT security. What are the OT environment protection strategies? So, there are many. As per some famous frameworks like IEC 62443 or NIST, or maybe some others, they have some foundational protection strategies. I have mentioned few of them. Identification, that's the most important strategy, protection strategy. So you cannot secure what you don't know exists in your network. So identification is very important. Segment assets into zones, so group by function, group by risk, or group by location. So segmentation is also very important. uh, Definition of conduits, or how the interzone communication will or should work. Always principle of least privilege should be followed. That is also uh, a good OT protection strategy, where you restrict the interzone communication, and you have defined the boundaries and conduits. Defense in depth controls, again using multiple layers such as firewalls, access controls, monitoring, physical security. If you have those layers, different layers, then defense in depth principle is being followed. And that is also one of the important protection strategies. Control, authentication, and authorization. You should always have least privilege enforced within the OT network, and a strong identity management solution should be used. Continuous monitoring is also very, very important. You have to detect what are the anomalous and suspicious behaviors in each zone within the OT network, and how to respond to those suspicious activities. So I would say these five or six OT protection strategies are the backbone for any strong OT cybersecurity program. Let's talk about uh, some of the principles behind OT-IT convergence. Uh, we are we are going to look at some of the most important developments shaping operational technology today, along with some emerging threats that every OT professional needs to understand. So here in this particular slide, I am showing you the convergence of IT and OT. So historically, these two environments existed in complete isolation, what we often refer to as an air gap design. There were no direct communication paths between the industrial systems and business networks, not because of the security policy, but simply due to the way these technologies evolved. So OT systems relied on proprietary protocols and purpose-built industrial hardware, while IT networks were built on open standards and commercial technologies. So when you compare the two environments side by side, the contrast becomes clear. So IT focuses on data, business applications, cloud services, virtualization, and OT, on the other hand, is centered around real-time control systems, physical processes, reliability, availability, safety. So OT systems use specialized equipment and industrial protocols which are built for safety and stability, not flexibility, which is the case with the IT side. So the push to connect these two words came from a growing business need, access to the operational data. So OT systems, they generate a huge amount of operational data, and organizations, they wanted real time insights to improve production, to improve planning, to optimize the performance, and to enable predictive maintenance. So this desire for data, commonly referred to as industrial digitization, it drove vendors to adapt industrial protocols for compatibility with standard IT technologies like TCP/IP. So this integration provides major advantages, but it also opens the door to new security risks. So uh, a decade or two ago, only a very small number of highly skilled groups were capable of attacking industrial systems. These operations require significant funding, access to specialized hardware, and deep domain knowledge. Uh, and but now the landscape has shifted dramatically. If you look at the number of documented OT or ICS cybersecurity incidents by decade, you see the growth. Huh? So in the 90s, or I would say in the 80s to 90s, you have only two major incidents on the OT side, and then you see a dramatic increase. So 10 around 10 incidents or more than 10 incidents in the 1990s, around 30 to 35 in early 2000s, and currently in 2024, close to 80 incidents have been documented. So there are several factors which are responsible for this explosion. So one is the IT/OT convergence has made industrial systems far more reachable, and the tools, the knowledge, and the exploits which were once limited to governments are now widely accessible. and there are criminal organizations, activists, ransomware groups, and even inexperienced attackers now target OT environments. So we see a tremendous increase in the number of ICS OT cybersecurity attacks year by year. Uh, why OT cybersecurity matters? Uh, so cyber attacks against industrial environments can have devastating consequences. I have categorized them into basically three major categories. The first one is the economic impact. So they can lead to costly downtimes, repair and replacement fees, or the costs will be too high if we have an OT attack, ransom payments, supply chain disruptions. So these are some of the economical challenges. Uh, then the physical consequences, you have safety incidents, environmental damage, equipment destruction, and risk to human life. Those are some of the physical consequences. And social and community impact also, public health risk, long-term service outages. So those are some of the devastating consequences when it comes to OT cybersecurity attacks. So that's it from today, guys. So OT cybersecurity continues to grow in complexity. The trends we have covered: greater connectivity, more capable threat actors, and increasingly sophisticated malware and global geopolitical tension. They all indicate that defending industrial systems will only become more challenging. So traditional approaches, like relying solely on the firewalls or assuming systems are air gapped, are no longer enough. So you need effective protection strategies, and you need a comprehensive layered defense strategy that spans industrial protocols, secure architecture design, network segmentation, monitoring and detection, safety system protections, risk assessment and governance. So these are some of the important points when it comes to building a strong OT cybersecurity program. That concludes this part on key OT concepts and terminology. Uh, it was a long one, but these fundamentals are essential as we navigate further. And in the next episode, we will shift our focus to the operational components, where we will talk about PLCs, HMIs, industrial controllers, and other assets that form the backbone of the OT systems. So, thanks for joining. I'll see you in the next module.